This conference will now be recorded.
Good morning, students, and we will start off from where we left last time. Last class, we were discussing about the deviations from Beer's law. So before that, we had seen what is Beer-Lambert's law, separately what is Lambert's law, what is Beer's law, and the form it is used in, that is as Beer-Lambert's law. It's taken in combination. So in short, what Beer-Lambert's law says is absorbance is directly proportional to the concentration provided you keep the thickness or the path length through the solution constant. And any deviation from this direct proportionality between absorbance and concentration is termed as a deviation or a limitation of this law. We have also seen that there were three different types of deviations. The first one being fundamental to the law. These are called the real deviations, and you cannot eliminate that. They have to be uh, kept in mind when you are applying Beer's law. This is mainly related to the concentration, and you should always use dilute solutions so that the substance obeys Beer's law. And the limit is usually given as 0.01 molar, so use concentrations less than 0.01 molar. We also had the instrumental deviations, which generally lead to negative deviations. That means you will be recording an absorbance less than the actual. And this can be eliminated to a great extent because this is mainly due to the presence of stray radiation or due to the use of polychromatic radiation. So if you use a good wavelength selector, you could make the radiation incident on the sample more monochromatic and avoid the problem. And also, if you reduce stray radiation by keeping all the transparent components clean, optically transparent, by maintaining them well, um, we can reduce instrumental deviations. And then the third one was the chemical deviations, which can also be kept to a minimum by ensuring that there is no change in the chemical nature of the compound that you are analyzing. So you have to have suitable conditions in your solution so that the compound remains in the same form throughout. So now we go on to application of Beer's law to single component analysis and then to multi-component analysis. Now single component samples means the sample has only one substance which is capable of absorbing. In such a case, what we do is first you have to run a spectrum. What is a spectrum? It's a plot of absorbance versus the wavelength. So where you get the peak, that wavelength, corresponding wavelength is the lambda max. So generally, we prefer to choose the lambda max for constructing a Beer's plot because it gives you maximum sensitivity. So this is a Beer's plot method where we prepare a number of standard solutions whose concentrations are known, and then we plot those concentrations versus their respective absorbance. That is, after measuring the absorbance in an instrument of each of these solutions, if you plot, you get a straight line curve. So this is what will give you the Beer's plot. We have seen this also. This is the standard Beer's plot, and here you have A equals ABC because Beer's plot says capital A equals small ABC. So small a, if you take on the left side, you get capital A divided by BC. Small a is the absorptivity. It is characteristic of a substance. So it must be the same at any point of the curve. So suppose you take at this point, you take the absorbance divided by the path length into the concentration, then you will get a particular absorptivity value. At this point also, you will get an absorptivity value. The two values should be the same. If it is a straight line, then the two values will be the same because the straight line will have the same slope at this point also and at this point also. And if the absorptivity remains the same, then we say Beer's law is being obeyed. Then, of course, I've told you earlier, from the absorbance of the sample, you see where it intersects your Beer's plot, and from there vertically downwards, you will get the concentration of the sample, and then you incorporate the dilution factor, you will get the concentration of your original sample. This was the Beer's plot method, and this is more accurate, less chances of going wrong because you are employing 4 to 5 standards. General practice is to employ 5 standards. So even if you go wrong with 1 or 2 standards, you have the other 3 to construct a proper Beer's plot, and chances of going wrong would be very less. There's also a slope method which I told you earlier, where you take the slope from this graph, and whenever you have a sample in the same solvent, you can just measure its absorbance and divide the absorbance by the slope to give you the concentration. So this is very accurate method. Second type of method for single component analysis is the specific absorbance method. What is specific absorbance? It's the absorbance of a 1% solution through a path length of 1 centimeter. So it's A 1%, 1 centimeter. 1 centimeter is in the subscript and 1% is the superscript for A. That is specific absorbance. 1% solution means 1 gram in 100 ml solution. So if you prepare a 1 gram in 100 ml solution and put it in a cuvette with the path length of 1 centimeter, then the absorbance that you measure would be the specific absorbance. Specific absorbance for different substances are standard values you will get from reference. So you can take that from reference and then compare with or use it in your method. So absorbance that you get for a given sample can be divided by the specific absorbance and then multiplied by the dilution factor. That will give you the absorbance of your sample. So here what we are doing is we are reducing the number of steps involved. In Beer's plot, you have to make 5 standards, take the absorbance of each, construct a Beer's plot, and then prepare your sample solution, measure the absorbance, and from the graph you find out the concentration. These are the number of steps involved, more tedious. Whereas in specific absorbance, you prepare a sample solution, measure the absorbance, you know the dilution factor, you know the specific absorbance of the substance. It's you'll get it from reference books, and when you divide your absorbance by the specific absorbance, then you will get the concentration. It's a very short method since you are preparing only one solution, but you need to be very accurate with the sample preparation. Even in Beer's plot, sample has to be prepared very accurately. Now, the other things which may go wrong is, while when you are doing the sample preparation, you are measuring the absorbance. Any errors or the instrument used, if there is any changes in the instrumental response, then that will get reflected as an error because you're using a standard method prepared under different conditions. Whereas in Beer's plot, both the standard and the sample are prepared and measured under similar conditions. So any differences will be duplicated in both of them. It's not so in specific absorbance. You are making only one solution and comparing with the standard value prepared under different conditions. So though it's a very fast method, it is prone to more errors. The third one is direct spectrophotometric method. Here you are going to be preparing 2 solutions, one sample and one standard. A standard of known concentration, whose concentration is known, and a sample whose concentration has to be determined. You measure the absorbance of both under similar conditions, and then you compare the absorbance of both. Since they are the same substances, the absorptivity will be the same, so you can reduce it to this equation. A standard by C standard equals A sample by C sample. Because you can write in this form for standard, and you can also write for sample in the same form. You will see the left hand sides are equal because A by B, B can also be taken here. So A by B will be common since A is the same substance in standard and sample. So left side hand sides will be equal, so right hand sides should be equal. And that's how you will get A standard by C standard equals A sample by C sample. Rearranging this, because we are interested in finding out the concentration of sample, we get C sample equals A sample into C standard by A standard. Now, this is a measured quantity because you have made your sample solution, you have measured the absorbance. This is also a known quantity because you have prepared the standard solution and you have measured the absorbance. This is also a known quantity because it is you have prepared the standard solution of definite concentration. It's known. So all these three are known. Putting all these values and incorporating the dilution factor, you can get the concentration of the original sample. So this method is also relatively faster compared to the Beer's plot method. There you were making 5 standards, here you are making only 1 standard. But this is ultimately proves less erroneous compared to this method, because here you are preparing only 1 standard. Any mistake in the preparation of the standard will reflect in the final answer for your concentration of sample. The sample may have been prepared very well, but one mistake, one small mistake in standard concentration will reflect in your final answer. This is not the case in Beer's plot method. You have 5 standards. One standard may be erroneously prepared, but the other 4 are proper. So you will get a perfect Beer's plot and a perfect concentration for the sample. So this is, of course, this is also a faster method compared to Beer's plot, but accuracy will go down and more prone to errors. And that's why in lab for students, this is considered a much better method, where initially you should get trained with Beer's plot method. As you become more and more, you do a number of these analysis, you can go to the direct spectrophotometric method and the specific absorbance method. Generally, it is these methods which are used in industry, but this also could be used because the standard plot is made and the slope is determined, and then you keep on doing your samples. Using the slope value, you find the concentration. So this was application of Beer's law to single component analysis. You have 3 different methods. Of course, most accurate is Beer's plot method. Now, we have to also understand that when you get unknown samples, it's very rare that you will be having a solution. You are given a sample which has only one component that absorbs at a given wavelength. There could be more than one drug, and now multi-drug treatments are very common. So combination drugs or combination formulations are also available. So how do you analyze? Is it possible to analyze using Beer's law? So now we go to multi-component analysis. The spectrophotometric assay of drugs rarely involves the measurement of absorbance of samples containing only one absorbing component. That means in our case, only one drug. The pharmaceutical analyst frequently encounters the situation where the concentration of one or more substance is required in samples known to contain other absorbing substances, which potentially interfere in the assay. That means there are more than one substance, okay? And you need to measure all, and or you need to measure only one, but the others will also interfere in your assay. So such samples are more commonly encountered. If the formula of the samples is known, the identity and concentration of the interference are known, and the extent of interference in the assay may be determined. So this is, if they are impurities, we call this impurity profiling. We can find out how much of each of the impurities are there and what is the impurity that is present. That's about impurities. But suppose you're talking about a number of drugs and you want to find out the concentration of each drug. You would have heard about tablets which have more than one drug. Say, for example, you have Calpol Plus, you all would have heard about Calpol, which has paracetamol alone, and you also have Calpol Plus, which has paracetamol with ibuprofen. So here we have two drugs. So it's a combination formulation, more than one drug. Now, if you use how do you find out paracetamol concentration and how do you find out ibuprofen concentration or the amount in a given tablet? So for that, we need to use Beer's law and apply it to multi-component analysis. So how do we go about doing this? So we'll take a simple case where there are two substances present in your formulation. Now, when we say that there are two substances, there could be different circumstances. Two substances with very different absorption spectra. You could have two substances with very different absorption spectra. What it means is that when you take a spectrum of this combined sample, you will get two spectra, which will be, that is, the peaks will be obtained at very different points. Something like this. See this, suppose you draw a spectrum, you get, say, peak for one drug, and then you get a peak for another drug. These two drugs are there, but they are absorbing at very different wavelengths. This is very rare, but it is possible to have like this. You may have nice tablets where you have paracetamol and nimesulide. So nimesulide is a colored substance, paracetamol is a colorless solution. So it will absorb in UV region, whereas nimesulide will absorb in the visible region. So in such cases, you will get spectra like this. And you can choose the lambda max or any wavelength corresponding to this to measure the concentration of the second substance, and you can choose a wavelength at this point to measure the concentration of the first substance. So at this wavelength, second substance will not show any absorbance. At this wavelength, first substance will not show any absorbance. So this is nothing but ultimately reducing to what we are actually doing is reducing it to single drug analysis. So first, though we have two drugs in solution, we choose a wavelength first at which only the first substance absorbs. Say paracetamol absorbs. In a mixture of paracetamol and ibuprofen, only paracetamol and nimesulide, only paracetamol absorbs. We choose UV wavelength such that nimesulide shows no absorbance. You measure the absorbance of your solution containing both paracetamol and nimesulide, but you will get an absorbance corresponding only to paracetamol concentration. Next, using the same solution but a different wavelength, a wavelength corresponding to nimesulide absorption, that is a visible light wavelength. It's roughly around 393 because it's a yellow colored solution. So if you use 393, it is a visible region because visible starts from 380. So paracetamol will show no absorbance at 393 nanometers. So now you choose the wavelength as 393 nanometer, use the same sample solution containing the mixture of compounds, measure the absorbance, you will get a different absorbance, and this will be for nimesulide alone. So this way we can apply Beer's law for each A equals ABC, and find the concentration of paracetamol from the first absorbance value and nimesulide from the second absorbance value. That's the first case. Next, you could have two substances with overlapping absorption spectra. So this could be of different types. See now here, suppose we draw like this. Here you have one absorbance, and um, here you have the second substance. These are overlapping absorption spectra. But here you can always find a wavelength, this wavelength, at which only the first substance absorbs. This is the first substance, this is the second substance. So the first substance absorbs at this wavelength. The second substance, you can choose a wavelength at this point, and you can measure the absorbance of only second substance, because first substance shows zero absorbance from this wavelength and onwards. So this also, though there is overlapping, it is possible to find a wavelength at which only the first substance absorbs, and here at which only the second substance absorbs. So this is also reducing to single component analysis. So here also there is no problem. But more commonly, what you will see is you may have a spectrum. When you take the spectrum of two substances, you may get a spectrum for the first substance like this, and you may get a spectrum for the second substance like this. Okay, so there is minimum absorbance here also. So from here to here, this is the absorbance range for the first as well as the second substance, but they show different absorbances at each of the wavelengths. So for this type of substances, now the matter is a little complicated. So how do we apply Beer's law? So here we will go further. So how do we do it? Compare absorption spectra of the two pure substances using epsilon values and superimposing the spectra. So what I showed you just now, a graph, you will superimpose the graph, so one over the other, and you will compare the two absorption spectra, something like this. This is molar absorptivity versus wavelength. You have two substances. You can see this line, this is for substance P, and this broad dashed line, this is for substance Q. Okay. You call it X and Y also, P and Q, but subsequently I think I've referred as P and Q, so you can take this as P and this is Q. And what is this small dashed line? This is for the mixture. If you take the mixture and analyze it, then you will get a curve like this, which indicates that it has both paracetamol and both P as well as Q substance. How do you get this P curve? This is by taking standard P solution. That is, you take the pure drug P, prepare a solution, and then you take the spectrum. That is, you at different wavelengths, you measure the absorbance and then convert to molar absorptivity, you will get a curve like this. Similarly, for standard solution of Q substance, you will get a curve like this. Now, if a sample contains two absorbing drugs P and Q, each of this absorbs at the lambda max of each other. You can see this is the lambda max of P and Q is showing some absorbance. Similarly, this is the lambda max of Q and P is also showing some absorbance. Okay. At lambda 1, this is lambda 1, this is lambda 2. It may be possible to determine both the drugs by the technique of simultaneous equation method, provided that certain criteria apply. The criteria, of course, is that first criteria is P and Q should not interact. Okay. The second things are, you have to select two wavelengths, lambda 1 and lambda 2. Like you saw in the previous here, suppose you're choosing this as lambda 1 and this as lambda 2. you have to choose lambda 1 in such a way that the absorbance of P is greater than the absorbance of Q. It is true, so you can choose it. Lambda 2, if you choose here, then you have to choose it in such a way that absorbance of Q is greater than absorbance of P. That's also true, so you can choose this. So here I have listed out the criteria. Select two wavelengths, lambda 1 and lambda 2. At lambda 1, absorptivity of P should be greater than Q, and at lambda 2, absorptivity of Q should be greater than P. Now next step is to construct Beer's plot for P and Q at both wavelengths lambda 1 and lambda 2. That means how many plots you will get. For standard substance P, you will construct a Beer's plot at wavelength lambda 1. That means you have P solution, you prepare a number of standard solutions, say 5 standard solution, 1 microgram per ml, 2, 3, 4, 5 microgram per ml of P alone. That is using the pure substance. So you have 5 standards of P. Using wavelength lambda 1, you will measure the absorbance of each of these. And you may get a curve something like this. So maybe you will get a curve like this at lambda 1 for P. Similarly, at lambda 2 for P, you may get a curve like this. For Q, you will again have 2 plots, one at lambda 1, maybe you get a curve like this, and at lambda 2, you may get a curve like this. These are all straight lines. I have not been able to draw it straight. So in each case, what you have to do is find the slope of each of these curves. So y2 minus y1 divided by x2 minus x1. Like this, you find the slope. The slope of this, now this was the curve that you got for P at lambda 1. So the slope is nothing but the absorptivity. So you will get A P at lambda 1. This is superscript, this is subscript. So the first absorptivity you will get from here. This was a curve that you got at lambda 2 for substance P. So the slope will give you A lambda 2 for substance P. This is at lambda 1 for Q. So the slope will give you A Q at lambda 1. And this is the curve at lambda 2 for Q, and the slope will give AQ at lambda 2. So now you get 4 absorptivities. I hope that is clear to all. So now we go further. So once we have calculated all this, now we go for sample analysis. So you will take your sample, which is a mixture of P and Q. You will measure the absorbance of the sample at lambda 1 and at lambda 2. So at both, you are going to measure the absorbance. So you will measure the absorbance at, there is some disturbance. Anybody is asking any question? So absorbance of the sample, which is a mixture of P and Q, is then measured at both lambda 1 and lambda 2. Okay. So you will get what absorbance you get at lambda 1 will be called A1, and what absorbance you get for the sample mixture at lambda 2 will be called A2. Now we already know that absorbance of mixture equals the sum of absorbances of all components in the mixture. Of course, we have assumed the components are not interacting with one another. So absorbance of mixture equals the sum of absorbances of all components in mixture. That means what? A1 equals A P plus A Q. Absorbance due to P plus absorbance due to Q. That is the total absorbance A1 for the sample mixture at lambda 1. Similarly, A2 will be AP plus AQ at lambda 2. Okay, so A2 is AP plus AQ at lambda 2. So it is again the sum of absorbances of the two components at a second wavelength lambda 2. So we have got these two equations. Now each of these absorbances we will expand it according to Beer-Lambert's law. So what is capital A lambda 1 P? Capital A for P at lambda 1 equal to, you will have to put equals epsilon BC. So epsilon for P, B, C for P. Okay, like this for Q also we will expand. You can see here A lambda 1 P equals, I've used here absorptivity, so you can use either absorptivity or the molar absorptivity. So absorptivity of P at lambda 1, B, C of P. Similarly, A lambda 1 Q will be absorptivity of Q at lambda 1, B, C of Q. And same for A lambda 2P and A lambda 2Q. So you now get the expanded forms. So A1 equals the summation of these two. A2 equals summation of these two. So using the values in equation 1 and 2, these values, we ultimately get these two equations. A1 equals absorptivity of P lambda 1 B C P. Now why we have not used lambda 1 here? Because concentration is not dependent on wavelength. Okay, whereas absorptivity is dependent on wavelength. And why we have not used any superscript or subscript? Because this depends only on the instrumental component, the sample cell, and the path length through the cell will be constant as long as you're using the same sample cell. So this is independent of substance, independent of wavelength, and that's why no superscript, subscript is put. So ultimately you get these two equations. So these two equations can be solved. Why? Because you see in these equations, this part, A lambda 1 P, this we have found from slope. Okay, this is a known quantity to you. This is also slope of another curve. This is a slope of the fourth curve, and this is the slope of the second curve. So you had all the slopes you have already determined. A1 and A2 you have measured. This is the absorbance of sample at lambda 1 and absorbance of sample at lambda 2. You have measured with your instrument. So these two are known, these two are known, these two are known. What about B? Generally, we take a path length of 1. Whatever it is, even if it is 0.5, it is constant. So this is a known quantity, you can disregard it. And remaining, what is it? CP, CP, CQ, CQ. These are the variables. These are the unknown quantities you want to determine. So it's like solving two linear equations. So you can, because something like 0.2 equals 0.01 CP plus 0.02 CQ. That's how you will get. And A2 may be 0.7 equals 0.03 CP plus 0.04 CQ. Solve the two equations, that is, make one equation coefficient same for CQ. It gets cancelled out. You'll get the value of CP. Put the value of CP in one of these two equations and you will get the value of CQ. So you can solve these two linear equations to get the values of CP and CQ. That is concentration of P and concentration of Q. So this type of simultaneous equation solving can be used provided you have two drugs or three drugs in solution. But when the number of drugs increases beyond that, it becomes quite difficult to use this simultaneous equation method. So there is another method which is called the graphical method. Now, if you see this equation, previous equation, this equation. Remove the subscripts because now we'll talk about, we are not going to include the wavelength. So this 1 lambda 1 lambda 1, if you remove, you will get the general equation like this. Absorbance of sample equals absorbance of P plus absorbance of Q. Okay. Now, if you divide both the sides by APB, so on the left side, you get capital A divided by APB equals, here since it gets cancelled, it will be equals CP plus, here divided by APB means B and B will get cancelled. What will remain is AQ by AP. So AQ by AP into CQ. So now you have to make a plot at different wavelengths. So how do you get these how do you make a plot? You'll make measurements at different wavelengths. So a plot of A by APB on the y-axis against AQ by AP on the x-axis. And you should get a linear curve, just like Beer's plot. But on the y-axis, you'll put this value. On the x-axis, you will put this value. And data points are taken at different wavelengths. You will get a straight line intercepting on the y-axis. So the intercept will be giving you the CP value, and the slope of the linear curve will give you CQ. So this way we can find the concentration of P and Q by graphical method. So this is also a method by which we can do multi-component analysis. So that completes the absorption spectroscopy, the general absorption spectroscopy that you have in your syllabus. This relates to different types of spectroscopy. So that's why it's a general topic. Now we have to next go into the instrumentation. Now instrumentation of UV visible region. So the instruments that are used in UV visible region. But before we go into the UV visible region, I will be also covering certain general instruments used in spectroscopy. Okay. So here we'll start with UV visible spectroscopy and the instrumentation part. So there are different types of spectroscopic instruments available to us. We have three different types of instruments. They are called the colorimeter, photometer, and spectrophotometer. Broadly, we have three types: colorimeter, photometer, and spectrophotometer. Now, colorimeter, what is the difference? Because these are asked in short questions, you need to be very thorough. This is a question that is also asked in your synopsis, in your practicals, and in Viva. How do you differentiate between a colorimeter and photometer, photometer and spectrophotometer, colorimeter and spectrophotometer? Okay, so we'll start with colorimeter. This is an instrument used for absorption measurements in the visible region only, using a filter as the wavelength selector. See, I had also already told you in the last class, absolute monochromaticity, to get that, we need to use purely monochromatic sources, which are only lasers. And lasers are very expensive and can be used only at one wavelength. If you have a laser as a source in your instrument can be used only for those substances which absorb at that wavelength. So the applicability of your instrument greatly gets reduced, and so it will not be practical to purchase such an instrument. Instead, if you have a polychromatic source and you use it along with a component called the wavelength selector, which isolates a few wavelengths around the desired one, then we can get almost monochromatic radiation, which is sufficient in most cases for spectroscopic measurements. And that's why the wavelength selector is a very important component. So if the wavelength selector is a filter, we'll subsequently see what this filter means. So if the wavelength selector is a filter and you are doing only absorbance measurements, that too only in the visible region of the electromagnetic spectrum, then the instrument you are using is a colorimeter. Okay, I hope it's clear. Next is a photometer. This is an instrument for absorption measurement or emission measurement or fluorescence measurement in the UV, visible or IR region using filter as the wavelength selector. Okay, so now here a photometer can be used for absorbance measurements. It can also be used for emission measurements or fluorescence measurements. And which radiation can be used in a photometer? You could use UV radiations, you could use visible radiations, or you could use IR radiations. But the wavelength selector is always a filter. So this is a photometer. What's a spectrophotometer? It could be used for absorption measurements, emission, or fluorescence measurements in the UV, visible, or IR region using a monochromator as the wavelength selector. So now the difference is in the wavelength selector. Instead of a filter, a monochromator is used. So if you see now the difference between a colorimeter and photometer, there are two differences. That is, colorimeter is used only for absorption measurements. Photometer is used for absorption, emission, and fluorescence measurements. Colorimeter uses only visible region of the electromagnetic spectrum. Photometer can use UV, visible, or IR region of the electromagnetic spectrum. What is the similarity? Both use filter as the wavelength selector. Then you have the spectrophotometer and photometer. Differences between these two. Both the difference is only in the wavelength selector. In the photometer, you use a filter. In the spectrophotometer, you use a monochromator. The similarities are both are used for absorption, emission, or fluorescence measurement, and both can use UV, visible, or IR radiations. So if you're using a UV radiations, you call it a UV spectrophotometer. Here, UV radiations, you call it a UV photometer. If you're using IR radiations, it will be called an IR spectrophotometer. Visible radiations with monochromator as wavelength selector, a visible spectrophotometer. Visible radiations with filter as wavelength selector, it could be colorimeter or photometer. Visible radiations with filter is wavelength selector, and only absorbance can be measured. It's a colorimeter. So I hope now it's clear the difference between these two. Whenever you have a monochromator as wavelength selector, the instrument will be prefixed by the term spectro. Remember that if you are calling any instrument by the word spectrophotometer, and subsequently in the next slide you'll see the spectrofluorimeter, it refers to an instrument where the wavelength selector is a monochromator. Okay, now we have seen photometer can be used for all these measurements. If it is specifically used only for fluorescence measurement, then it is called a fluorometer, a fluorimeter, or a fluorophotometer. And if a spectrophotometer is used only for fluorescence measurement, it's called a spectrofluorometer, spectrofluorimeter, or a spectrofluorophotometer. So again, like I told you, the term spectro is used. That means the wavelength selector in the instrument is a monochromator. And if you don't have the term spectro, then it's a filter which is used for wavelength selector. So these are the different types of instruments that you come across generally in UV visible spectroscopy. Now the basic components in this, I think we can continue in the next class. So do you have any questions, anything which is not clear to you from today's portions, what we have covered in today's portion? Do you have any doubts? Could you understand Everything?
Yes, ma'am.
Was I audible?
Yes, ma'am.